Thanks for the introduction.
Is it still recording?
On behalf of the University of Turin.
Yes, it is.
Recording? Yeah.
I think so.
Today I'm going to present an officer titled A Novel Approach for Beam Characterization and Online Monitoring in Particle Therapy. Okay. The line of this talk is divided in 8 points. First, I'm going to summarize briefly we monitor for particle therapy through the last project that we are working on, the MOVIT, FRIDA, and SIG-INFM project. I will summarize the sensor production by FBK together with Italian facility dedicated to particle therapy, where we test all device. I will summarize the method that we use for calculate the energy of the beam using time of flight, also the particle counting capability. At the end, I will summarize briefly the thin silicon sensor that we use for tracking carbon ion and silicon device for monitoring electron proton flash beam. In the last year, the University of Turin has been working in beam monitor for particle therapy to overcome the limitation of the ionization chamber using silicon device. Within the MOVIT project, 2 devices were developed based on long-gain avalanche detector. One is able to directly count individual proton at high fluence rate in an area of 3 by 3 centimeters square, being segmented in a strip, so allows us beam projection into orthogonal directions. The second device is able to measure the beam energy using time of flight technique with an error of less than 1 millimeter of water range. Today, the ionization chamber are the one are monitoring the system. They are robust, have simple construction, free out, large sensitive area, and radiation resistance, but they suffer like low correlation time, low sensitivity, and dependence on beam energy environmental parameter. So, due to the challenge of pencil beam scanning, these devices are not appropriate for fast scanning modality and timing application. And one alternative is use solid-state detector because they are fast, collection time of the order of nanosecond, excellent time resolution, good sensitivity that allow us a single proton detection. But there are so many issues like high fluxes, like radiation resistance and pile-up effect. Within the solid-state detector, we are using ultra-fast silicon detector, which are based on long-gain avalanche detector. I'm not going into detail because yesterday was very well explained. So I'm just going to point out that there are this detector gives to us a fast signal duration of the order of 1 to 2 nanoseconds that provide us a single particle detection capability. And also there is a good time resolution of the order of 10 of picosecond, which is optimal for energy measurement using time of flight technique. The other project that started this year and we are working on is called SIG, which stands for Superconducting Ion Gantry. It's an international collaboration which its main goal is to develop a compact ion gantry based on novel curve superconducting magnets. The Torino Medical Physics Group are in charge of develop new technology for those delivery systems. Basically, develop new beam monitor able to track carbon ion using segmented thin silicon sensor with advanced front-end readout and that system to provide the timing of crossing information. The second project that we start also this year is called FRIDA, which is flash radiotherapy with high dose rate particle beam. As all of you No, the current monitor solution lacks the necessary precision to give robust estimate of the instantaneous and average dose rate needed to characterize the flash effect and to provide the reliable feedback on the radiation delivery during the treatment. So the University of Turin is studying a thin silicon sensor and associated electronic for electron proton beam monitoring in high dose rate regime. In 2020, the university, this goal of this project cannot be done with the close collaboration that our university has with FBK, located in Trento, the sensor manufacturer. In 2020, we have a production of 14 wafer tailoring for the counting prototype facility, prototype equipment. On the left top figure, you can see different sensor geometry. The sensor labeled with the letter A is the sensor used for timing counting purpose. You see here the dimension of the sensor with 2.6 by 2.6 centimeters square of sensitive area being segmented in strip, 146 strip. On the middle image, you can see the strip segmentation of this sensor. There are another sensor with another geometry like B, E, and F, mainly for testing purpose on laboratory. This production has two different active thickness, 45 and 60, and you can see this table for more detail. There are another sensor, the one on this page, labeled T, is the one we use for timing purpose. It's segmented in 11 strips, as you see here in this picture. Each strip having a sensitive area of 2.2 millimeters square. We have at the end of this year, there is a sensor production ongoing thanks to a colleague, Valentina Sola. These sensors are for monitoring flash beam. There is with four different beam, different substrate thickness from 15 to 45 micrometer, and very small sensitive area from 2 millimeters square. That is more or less the area of the timing sensor strip, up to 0.03 millimeters square. So it's very, very small. The Italian facility dedicated for particle therapy, where we test our device, the one is located in Trento, in Italy, is a Trento proton therapy facility based on the cyclotron, when the maximum flux that can reach for proton is 10 to the 10 proton per second, with the energy selection between 70 and 228 MeV. I would like to point out that at the end of 2022, this year, for the larger energy, there are a grade of ongoing that can reach, as expected, is expected to reach 10 to the 12 proton per second to be able to make a flash studies with proton. The second center that we test our device is a national center for oncological atom therapy, based in synchrotron with a diameter of 25 millimeters, where it can accelerate both proton and carbon ion. The proton can reach to a maximum flux of 10 to the 9 proton per second with the energy between 60 and 230 MeV. Instead, for carbon ion, the maximum flux can reach to 10 to the 7 carbon per second with the energy between 120 and 400 MeV per nucleon. Here I'm going to summarize how we can calculate the energy using time-of-flight technique. First, we place one sensor at the isocenter and a second sensor to a known distance from the sensor one. In the middle image, you can see when we select a sensor, this peak represents the proton that we are reading out from our silicon device. In the x-axis is the sampling half of the events of the digitizer. Each sampling represents 0.2 nanosecond, and the vertical axis is arbitrary unit. When we select a peak, like for instance, the blue one, on the first sensor, higher than the threshold, we activate a looking window. So in this looking window of 10 nanoseconds, we look in the second sensor a peak higher than the threshold. When this peak, as you see in this window, is selected, we make an histogram of the number of coincidence versus time difference. This peak, we apply constant fraction discriminator algorithm to avoid time walk effect. When the blue arrow is pointing out the true coincidence, instead the red arrow is pointing out the false coincidence. Like taking the time, taking this distribution, the time of taking the proton to pass from the first sensor to the second sensor, so it's a coincidence, the same proton, and knowing the distance between this sensor, we can get the velocity, the energy, and therefore the range in water that is the interesting parameter for the clinic. This method, this approach is very sensitive to the picosecond level, so we need to calibrate our system in order to correct this systematic error like the offset due to the cable and also the distance between the sensors. So we developed a method we call relative calibration. Is based on chi-square minimization, where this method, for more information, you can follow this paper here we published. There is a limitation of this method that you need to know beforehand the nominal energy of the facility. So there is a limitation here. For that reason, we move forward. We create a new method. It's under patent process with self-calibration that you don't need to know anything about the facility. So it's based on the relative displacement of the second sensor. Here is the experimental setup that we use with our prototype. We read out, you see here, each sensor with a custom front-end board with 2 stages of amplification that give it to us a gain of 100. And the output of the sensor of this board is read out by the high rate kind digitizer with 5 gigasamples per second, read out with optical link with the computer for the offline analysis and control acquisition. On the bottom image, you can see our prototype. You see the yellow arrow is pointing the beam direction, and the sensor one is placed at the isocenter. We see here we can control this device remotely. We can change the distance between the sensor between 20 and 100 centimeters. And the second sensor can move with the stage motor in X and Y direction to alignment. The main result for the time of flight prototype can be visualized in this slide. For instance, on the left, we can let's summarize in the horizontal axis. You can see the nominal energy, and in the vertical axis, in the both plot, you can see the difference between the nominal minus the measured energy, the energy that we get using our device. As you see in this plot, for instance, at the now facility on the left, we see the dashed line are their error range between 0.1 millimeter is the first dashed line, and the second one, the far dashed line is 1 millimeter. And you see for the 3 different distance, we obtain an error less than 0.5 MEF for all the energy or for all the distance between the sensor. Or for the larger distance, the blue one, all the error taking into account the range is less than 0.5 millimeter. On the right, happened the same. We tested at Trento Proton Therapy Center, and we obtained for all the distance an error less than 0.5 millimeter of range. I would like to point out that our prototype is almost transparent for the beam with an error with a perturbation around 250 micrometer of water range equivalent. our measurements are very fast. Only a few milliseconds of data was necessary to obtain the accuracy of our prototype, and was tested in two different facilities. So there is an independent of the beam time structure. So one of the applications can be for beam commissioning in fast QA procedure. Now I'm going to talk about our second device. Basically, we developed a chip that are able to count at heart rate the signal coming from the sensor. You see here is based in 110 nanometer CMOS technology with a chip area of 2 by 5 millimeters square, having 24 identical channels with a dead time of 10 nanoseconds. Yes, charge sensitive amplifier. Dynamic rate range of between 4 femtocoulomb to 150 femtocoulomb. Basically, how is connected the signal from the sensor is wire bonding to a channel input. For instance, this is an example of one channel is integrated over a sensitive charge sensitive amplifier. After passing for low pass filter, non-inverting low pass filter, we amplify the signal. We make a shape of the signal. Before the discriminator, this part, when the signal is higher of the threshold on the discriminator, leading edge discriminator, we divided the signal into paths. One path is for discharging the capacitor to baseline restoration to prevent saturation of the electronic. In the second part is passing outside of the chip to FPGA through the CML signal. This is the particle counter prototype we developed using the same chip that we test with 24 channels. We place in this board that we call ESA Abacus. We place 6 chips, as you see here. Each chip can control 24 channels. So in total, with 6 chips, we control 144 channels. This means 144 strips can be read out with this approach. And we use Kylin FPGA to control, to read out the transition of the threshold 0-1 to count every proton, and set the external threshold to properly count the proton. And the last program is made to control the precision, save the count and the timestamp of the FPGA. This is the experimental setup. As you see here, the red arrow is pointing out the beam direction. We use 2 boards. The board A is placed at the isocenter, and the board B is placed at the relative distance from the board labeled A. I forgot to say that our device, our silicon sensor has 146 strips, but we are reading out the digital channel only 144 strips, but we have on the edge of the board 2 strips that are read out analog, so to see the signal shape on our detector. So this was the main reason of use the board B in this experimental setup. The main result from board B using the analog channel can be visualized in this slide. For instance, here in the vertical axis, you can see the amplitude in millivolts, and the horizontal axis, you can see the time in nanoseconds. So the sharp peak represents the detected proton, and we made our experimental with using LDAT strip and a simple silicon sensor. As you see, a very big peak will be visualized in the LDAT strip instead for this small peak here representing a proton when we observe in the normal silicon sensor. On the bottom plot here, you can see the number of peak versus peak amplitude, where you can see a good separation between the noise and the signal here. So selecting a proper threshold, you can count properly the proton. Instead, when you use a standard silicon sensor, you see that you cannot properly separate the proton. So the proton is going to the noise region, so you are not able to get useful information there. In the top image, you can see the most probable value versus reverse bias for the LDAT strip for different bias voltage. So you see an exponential increase due to the gain layer. The main result from board A using the digital channel, you can appreciate in this slide, we use 5 10 to the 8 proton per speed. You see for 3 energy, 62 MeV, 115 MeV, 226 MeV. You see there is 3 peak here. That is to no uniformity channel that we are going to correct very soon in the next beam test, because we can correct it on the chip. You see that we properly see the beam shape for the 3 energy. On the bottom right image, you can see the full width half maximum mean in 20 equal speed versus the energy. We compare this with the bibliography. We see a very agreement with the data to 115 MeV, something that we don't see for the lower energy. This is because we are losing the tail of the beam. So this is a work in progress. We tested for different degraders from 20 to 100 and for this number of proton per speed. Now I'm going to talk about the thin silicon sensor for carbon ion charging preliminary test and now. I'm not going into detail here because more or less the same setup that we used before using timing. We are using the same board. The only difference is instead of use a LGAT sensor, we are using a standard silicon sensor. So there is no gain layer implanted in this sensor without with the current digitizer. We tested for 4 different beam energy from the higher energy to the lower energy provided at now for different bias voltage to different positions with respect to the beam direction, 0 and 40 degrees. This is an example, as you see, for bias voltage of 149 volts, and for the higher energy provided by the facility, you see in the vertical axis on the left plot, the amplitude versus time for a time window of 30 nanoseconds. You can see very well the sharp peak that represents the carbon ion passing through our detector. On the right plot, you can see the number of peak versus peak amplitude for the A strip that we are reading out with our electronic. You see a good separation between signal on the left and between the noise and the signal here. So selecting the proper threshold, you can easily count the carbon using this setup. I would like to point out this. We fit it with the convolution between Gaussian and Landau function. We get the most probable value. The difference between most probable value was between 0.22 volt and 0.24 volt, and this difference because we are expecting the same, all the distribution aligning the same point. This difference is due to electronic, the tolerance of the components that give to you this chip. We test our device for most, here we can observe the most probable value versus the energy for 2 strips and example for different bias voltage. As you see, for instance, let's see this point here, lowering the bias voltage, we are getting a lower most probable value, and this is because no saturation of the drift velocity for electron mainly. On the right plot, you can see the most probable value versus bias voltage for different position of the sensor. One position in 0 degree, in one position 40 degree. As you see, when we put the sensor 40 degree, there is an increase of most probable value, and this happened exactly we obtain a ratio of 1.26, and this happened due to the larger path of the carbon in the active area of the sensor, so you are crossing the sensor in the diagonal path. Exactly, we measure with this ratio 38 degree of inclination of the sensor. We put in 40, we have an error of 1 degree, let's say. And finally, I would like to introduce the silicon device for monitoring electron proton flash beam. We use also the same detector, the layering strip, segmented with 2.2 millimeter square of active area, being segmented strip, as you see here, and we can read out this sensor with a custom electronic that was developed by our group. It's a current to frequency converter. It's called Tera08. It's based in the recycling integrated architecture. So we are splitting the signal of the sensor in 64. So doing that, we are increasing the capability of the electronics so we can reach in each strip 256 microamp. So we are a very high range of integration. Here are the results in electron measurement at the Electa SL18 Linux that we have in our university. We can see here the measured current on the silicon strip versus the gray per second at the isocenter. You see for three different energy, 4, 6, and 10 MeV for 2 different days. We see a very nice linearity of our data. You see, this confirms good linearity because we made a linear fit with 0.99 R squared. And also the reproducibility of our data because we made this test in 2 different days and we obtained the same. On the right, we can see the proton measurements, and now we can see the measured current per spin on the silicon strip versus proton per second. Give it to us for the dose delivery system. We tested for 3 different energies, 60, 115, and 170 MeV. For the different color, red and black, is read out with the 2 strips read out with different chip. The difference here in the slope is because the strip is put in front of the beam in different positions, so you have a different flux coming inside of the silicon sensor. Finally, I would like to make a fast introduction of the preliminary result on the modified Electa SL18 Linux. It's a work ongoing. This result we got 2 weeks ago. As you well know, having a facility that provides us a flash beam is very expensive. So we decided to follow this paper performed where the author report the modifying clinical linear accelerator for delivery ultra-fast, ultra-high dose rate irradiation. So we did the same modification. We are performing the same modification because they have a similar accelerator. So we follow this to perform an upgrade of the energy of the Linux or Linux. So basically, we use a standard silicon sensor with this strip area 2.2 with this active thickness. No detector bias needed for the larger energy. So the Electa technician came to our university, performed basic modification to the Linux, such as they changed the setting, like the setting for 10 megavolts of X-ray. They put in on the setting of the 10 MeV electron, and also there is no filter on the path of the electron. And also they optimize the coupling between the radio frequency of the magnetron and the gun current to get more power on our machine. Also, with what happened, we need to develop also electronic able to count the pulse of the Linux to interrupt the Linux before the interlock of the ionization chamber. So we made an in-house circuit based mainly in amplification path, Smith trigger, as we know, nano, and also a relay that is interfaced with the Tylotron trigger signal to prevent any trigger reach the magnetron. So here is an example, for instance, of 7 pulses that were requested. Here on the top image, you can see on the normal condition, 7 peak. We see here clearly 7 peak in our device. This is read out with the electronic that we said before, the Tera08 chip, because we use this sensor placed behind another sensor to control the pulses and another sensor used for read out this, the current, like you see here. In the bottom, we can see the modification of the Lina with the flash setting was made. You see 7 peak, and there is a factor of 100 with the new setting. Finally, I would like to make the remark and conclusion. The LDAR technology can be used for beam characterization or line monitoring of proton beam. The measure energy using time of flight were independent with the beam energy with the beam time structure, and only a few milliseconds were necessary to achieve 1 millimeter range precision. For the first time, LDAR sensor with a large sensitive area able to cover the entire beam spot at the isocenter were tested with clinical proton beam and now. The results show good separation between signal and noise in the LDAR state, a feature not seen on the beam. Using a 2.6 by 2.6 centimeter square LDAR sensor, the proton counter was able to replicate the beam profile to at least 150 megs. Preliminary tests in thin silicon sensor for single carbon ion detection on clinical beam were performed and now, showing very promising results and preparing the groundwork for future development of the counter and beam energy detector specifically developed for clinical carbon ion. And finally, preliminary tests with electron proton using conventional dose rate and intensity respectively confirm the linearity and reproducibility of the system. In addition, an upgrade of a modified Electra SL18 Lina is ongoing. Finally, a measured current per pulse increased by around a factor of 100 of the first upgrade attempt. Thank you.
Okay. Thank you. Thank you, Oscar.